Welcome back. Let's do another mesh current problem. And this one talks about superposition a little bit more. Okay, we've got this circuit that we're given. We have a 60 volt source here. Resistor. Oh, resistor down here too. Then another resistor. Then one of these guys again. Then another resistor. So this is a 20 volt source. This one's a 3 ohm resistor, a 2 ohm resistor, a 4 ohms resistor, 10 ohm, 1 ohm, 60 volts. Okay, you're given these mesh currents. So this is I1 mesh current, and then you're given this. So let's I1 and I2 mesh currents. Let's look at them. They agree with the signs on the on these independent devices, right? We've got the current coming out of this terminal going around that way, and that's good. That's going to cause less confusion later if we make those guys agree. And same thing here. We've got this guy coming this way out of the positive terminal. Now, as long as you follow the rules with signs when you write the equations, you can do these in different ways. It's just you'll have negative signs running around that you gotta reconcile, and it gets confusing. So you try and set these up so that they line up right. Okay, there's another level of concept that's going on in this problem. These I1 and I2, these are mesh currents. Okay, so let me write that down. You're given I1 and I2 mesh currents. These are mesh currents, right? And what you're asked to find on this problem is, well, branch currents, which I haven't drawn yet, but here, there's one here. This is IA. This is IB. And this is IC. You're asked to find the IA, IB, IC branch currents. So there's a difference between mesh currents and branch currents, and that's the superposition thing. So let's, talk about that a little bit more. So basically we got mesh current versus branch current, and who wins, So let's say you had this deal here. You've got, say, I1, and then let's say you put these going the same way. Let's say you did that. Then, oops. Yeah, well, I meant to do this. Look, I don't want to scribble on it. Let's say you make them going this way, I1, and this one going this way. Let's say you did that, which is like the problem we have set up. Then the branch current, let's call it let's use IB here. So IB is I1 plus I2. This is superposition, really. So the branch current is the total current. That's the total actual current in the branch. That's why they call it the branch current. And the mesh current is just the current that's used to write the mesh equation. It's a partial current. It's a partial current used to write the mesh current equation. Okay? So if they were green, you'd add them, and then here they're disagreeing. So here, if this is I1 or B, let's call it IB. If IB is going to be I1 minus I2, right? So this mesh current versus branch current. Branch current is the total current, the actual current that's going through there. But the method that we use, the mesh current method, uses these partial currents called mesh currents, and we add them together. We add the final currents together. We add the effects of the currents while we're doing them. We're also going to add, IR effects, for each mesh current. We're going to do that. So let's do that. Okay? So we'll write mesh current equation 1 So remember, when we do mesh current, what we're doing is we're summing the voltages equal to 0, but we're using V and IR terms. Sometimes we'll use V terms if we have them. Other times we'll use IR terms if we don't have the V term directly. So go around this guy, come in the negative sign, so it's negative 60. Okay, then we typically, just the resistances are going to be positive voltage terms because they resist the mesh current. So there's really no reason to write the plus minus plus minus plus minus. You can just write these guys directly. So this loop going around here, it's 4I1 gives you a voltage drop, 10I1 gives you a voltage drop, 1I1 gives you a voltage drop. So it's 4I1 plus 10I1 plus 1I1. These are the I1 effects. Okay, then you got to use superposition. You got to add in the effect of I2. Okay, so there's going to be 10I2 voltage. This is IR, so this is a voltage. All of these are voltages, but this voltage term is due to the I2 mesh current, and these two are going in the same direction. So this is a positive sign. So this is positive because I1 and I2 are the same direction. Okay, that's mesh current equation 1. Then we can write mesh current equation 2. So we go around this loop and we're coming into the negative sign. So it's negative 20, and then it's going to be voltage drop across the 2, across the 10, across the 3. Those are all positive. It's going to be 2I2 plus 10I2 plus 3I2. These are what I like to call the I2 primary effects. Then you apply superposition. This was I2 effects over here. Now we're going to do 10I1. We're going to do the effect of I1 across this 10, right? And it's positive because they agree. Same reason. It's this. Okay, and those sum to, both of these sum to 0. Okay, there's two equations, two unknowns. So there's two EQs, two unknowns. So there's a solution. So this, we put it in standard form. I'd like to see your stuff in standard form so that I can grade it a little bit easier. This ends up being I1 15 plus I2 10 equals 60. That's if you factor out the I1 and add up all the junk. And then this was equation 1, and then equation 2, this guy here ends up being I1 times 10 plus I2 times 15, and that equals to 20. And then my calculator, says I1 mesh current equals 5.6 amps, and I2 mesh current equals minus 2.4 amps. Okay, so this method gives you mesh currents. You write the equations in terms of the partial mesh currents, and then it gives you answers in terms of those mesh currents. But we're asked to find the branch currents. Okay, so we'll do that. But look, this was negative before I move on. This was negative, which basically means that we chose poorly, right? That we chose correctly on this because it's 60 volts, but this 20 volts, and it's not easy to see. It has to do with, how the resistor network values are and stuff. But it turns out that the actual current, the actual mesh current is going the other direction, but that's fine. So we can solve for the branch currents. So some of them are the same, like IA is simply I1, right? Because IA is just through this side of the thing. It's just around in here, in this branch, right? It's just in this branch, right? The current through these 3 wires is a branch. It's called a branch. It's all the same current, but the current through this branch is different. Right. So this one here is the same. It's 5.6 amps. That's the answer. But IB is, there's two mesh currents that go through that. So I1 agrees with IB, so it's going to be positive. I2 is the opposite direction of IB, so it's going to be negative. So it's going to be 5.6 minus, what is I2? I2 is negative, whoops. These agree. I1 and I2 agree. This should be a positive sign. Sorry. These are positive. So it's positive, because you have to go by the arrows when you write these. You go by the arrows when you write equations. You go by the arrows and then the plus minus signs when you write them. But then when you put in the values, you go with the sign that's on the value. So this is minus 2.4. So this ends up being 3.2 amps. A little, like I say, these negative signs are inherently a little bit confusing. So IC is, through these three guys as IC, happens to be, for this part of the circuit, just these three guys, it happens to be the same as I2. So it's just minus 2.4 amps. Yeah, that's what it is. All right. That was a mesh current versus branch currents. It's all about superposition. Basic idea of which is you treat these mesh currents independently when you write the equations, and you add in the effects of the other mesh currents, and then but if you need the actual total physical current that's going through a particular branch, you need to reconcile the mesh and branch currents. Sometimes they're the same if that's the only thing happening. Sometimes it's the sum or the difference if they agree or if they disagree. They agree or they disagree. All right. Hope that was helpful. See you next time.